All right, objective 4.1, we are simplifying rational expressions. Okay, now like it says right here, the term rational expression is just a technical term for what you know as in other words, it's just a fancy word for fraction. Okay, so again, rational expression, just a fraction. The only difference with these fractions is that most of them are going to have variables. In other words, they're going to have polynomial expressions. Might be a monomial, might be a trinomial, might be a binomial. It could be any of those things, but we're going to start seeing variables in our fractions. Okay, and then like a numerical fraction, a rational expression is undefined when the denominator is zero. The value or values that make a rational expression undefined, in other words, the values that make the denominator come out zero, we call those excluded values. And so excluded values, again, are just the ones that make our denominators come out zero. We don't want those. We want to exclude them from our answers. Okay? All right, let's jump into some examples. So number one, we want to simplify 20 over 8. Okay, so how do we simplify something like 20 divided by 8? Now this is, fairly easy. You guys have been doing these for a while. But we want to see, how it works because it's going to make the rest of these problems make more sense. Before I start reducing, let's write 20 a different way. Let's see, if I wrote 20 in completely factored form, so if I broke down the number, let's see, 20 is, 5 times 2 times 2. Okay, so if I completely factor 20, I get 5 times 2 times 2. And then what if we completely factor 8? 8, let's see, that's just 2 times 2 times 2. Okay, and then what do we have in common on top and bottom? Well, I got a bunch of 2's on top and bottom. And since I'm multiplying, I couldn't do it if I was adding or subtracting. But since I'm multiplying these numbers together, then I can reduce. Now, technically, if I cross off these 2's, well, they don't just disappear. This turns into a 1 and this turns into a 1 because 2 divided by 2 is 1 over 1. But we don't normally have to write the 1's. We can just cross them off. That's fine. I got another pair of 2's that, again, technically reduce to 1's. And then, well, what's left over? In other words, what is my answer? Well, 5 over 2. Okay? And then that's how we're going to do all of these expressions. We're going to get them in factored form, see what we are multiplying on top and bottom, and then reduce those. Okay, and then whatever's left over is our answer. So our answer here is just 5 over 2, which, yeah, I can divide the top by 4 and the bottom by 4, and I'm left with 5 over 2. That's how we normally do it. We're just looking at it, in a different way here. All right, so the next one, 12x to the third over 3x. Let's center this here. Okay, how do we solve that one? So again, we can just reduce like we normally do. But another way to write this, let's see, 12 is 3 times 4. And then 4 is 2 times 2, so how about 3 times 2 times 2, completely factored. And then we have x to the third. How can I rewrite x to the third in factored form? Well, x to the third means x times x times x. So we can write it out that way if we want to. Over, and then 3 times x is just 3 times x. And then let's see, what do we have in common on top and bottom? Well, those 3's reduce, so I can get rid of those. And then I can cross off this x and one of those 3 x's. Okay? And then what are we left with? Whatever we're left with is our answer. Well, on top of it, got 2 times 2, which is 4, and x times x, which is x squared, over 1, which we don't need to write. That's our answer. It's just 4x squared. Okay? So again, different ways to do it. We don't always have to write it out completely like that if it's something like this, but hopefully that makes sense. Okay? Moving on to the last one. Okay, now here, we got x squared plus 7x plus 10 over x squared minus 4. Well, let's see, they both have x squared. Can I just reduce those? No, because we're not multiplying those. Okay, and if that doesn't make sense, grab a piece of scratch paper real quick. Write out something else. Let's see. Let's just make this up real quick, 6 divided by 2. Okay, 6 over 2, well, we all know that equals 3, right? Okay, that's easy. Can I rewrite 6 in a different way? Sure. How about 4 plus 2 over 2? Okay, well, now I got these 2's. Can I reduce these 2's and turn them into 1's? Well, then what do I get? 4 plus 1 on top, which is 5, over 1, so my answer is 5. Well, is the answer to this thing 5? No, it's 3. Okay, so again, we can only reduce when we're multiplying. One more time, 6 divided by 2. How about if we write 6 as 3 times 2 over 2? Then can I reduce the 2's? Well, sure, because if I reduce these, I get an answer of 3, which we know is the actual answer. So anyways, just a quick demonstration of why we can reduce when we're multiplying, but not when we're adding or subtracting. Okay, so I cannot reduce these things because it's x squared plus 7x plus 10 and x squared minus 4. So first thing we want to do is factor this problem. So let's see on top, x squared plus 7x plus 10. I want to factor that into two binomials. I know the signs are the same and they're both positive. So plus and plus, got x times x. And then what multiplies to give us 10 and adds up to 7, 5, and 2. Okay, over, and then on the bottom we've got a difference of two squares, x plus 2 times x minus 2. And then what do we have in common on top and bottom? The x plus 2's, I could reduce those, and again, we don't need to write the 1's above them, but we know technically they reduce to 1. And then what's our answer going to be? We'll squeeze it in below here, x plus 5 over x minus 2. Okay, so just like the other problems, we factor, reduce whatever we can, and whatever's left is our answer. Okay, all right, zoom out a little bit. So, as it says, you may have noticed that there is going to be a lot of factoring involved. So let's review factoring again, because we reviewed it last chapter as well. So first thing we should always check for, unless it's factoring by grouping, is a GCF. We always want to see if we can take out a GCF first. Next, what if we have a difference of two squares? So something in the form a squared minus b squared. How is that going to factor? Well, that's going to factor into a plus b times a minus b. And the order doesn't matter. You can go a minus b times a plus b. Okay. Trinomial factoring, that could be with or without a leading coefficient. That's just the normal factoring here. Perfect cube factoring, so it could be a cubed minus b cubed or a cubed plus b cubed. How's that going to factor? Well, that's the one where it's a binomial times a trinomial, and we like to use SOAP to get our signs. Okay. Now, just so we can write it only once, let's use a plus or minus symbol instead. So it's going to be a plus or minus b times a squared plus or minus ab, and then always plus b squared. Okay, so we'll use that occasionally, and then factoring by grouping is what we use when our polynomial has 4 terms. Okay, all right, let's look at some more examples. Pretty much just going to practice some of this stuff. Let me zoom back in so we can see the problems clearly. All right, so first one, a squared minus 4a minus 21 over 7 minus a. Now, again, the first thing we want to do is factor, because I can't reduce when I'm adding or subtracting things. It's got to be multiplying. So on the top, how do we factor a squared minus 4a minus 21? Let's see. It's going to be two binomials. To get a negative 21, I got to multiply a positive and a negative. I got to have a and a to get a squared. And then what multiplies to 21 and has a difference, since my signs are different, of 4. Well, 7 and 3. The bigger one needs to be negative. So 7 and 3. And then on the bottom, I've got 7 minus a. Is that going to reduce with this thing? No, almost. What's the only thing I want to change? Well, the signs, right? So to change the signs, like we said in the last chapter, we want to factor out a negative. So I can take out a negative 1, and then that would leave me with positive a and negative 7. Okay, and then now we can reduce these things because now they match. And then we're left with a plus 3 over negative 1. So we can just write that as negative a plus 3. Or if you don't want to have the negative on the outside, you can distribute the negative and get negative a minus 3. Either one's fine. Okay, so there's that one. Moving along. 7x squared plus 23x plus 6 over x squared plus 2x minus 3. Again, since we're adding all this stuff and adding and subtracting this stuff, I can't reduce yet. Got to get it in factored form first. Okay, now looking at a problem like this, which part is going to be harder to factor, the top or the bottom? Probably the top, because of the leading coefficient, right? Now keep in mind, in this whole section, in this whole chapter, the reason we're factoring is so we can reduce. So these problems are going to be set up so that usually something is going to reduce. So let's factor the easier one first, because that'll give us a clue as to what one of our factors will probably be up here. Okay. In fact, I may have had a typo there. Oh, no, sorry, because it's the leading coefficient. Okay, so let's start factoring, and we're going to start on the bottom. All right, so x squared plus 2x minus 3. Well, that's going to factor into two binomials. My sign's got to be different. Got to have x and x. And then, excuse me, our number's got to multiply to 3 and have a difference of 2. So it's going to be positive 3 and negative 1. Okay, so then we got the bottom factored. And then again, like I was saying, I know this thing's going to factor into two binomials as well. Well, most likely, one of those binomials is either going to be x plus 3 or x minus 1, because if neither of these is one of these two things, well, then nothing's going to reduce. So we're guessing that one of them is probably going to be one of these things. Okay, and let's see which one. I know my signs are the same, and they're both positive, so plus and plus. Okay, now already, which one does it have to be on the bottom? Well, since the signs are both positive, it's got to be x plus 3 because there's no negative up here. So I'm guessing that one of my symbols is x plus 3, one of my binomials, I mean. And then let's see, let's just fill that in and see what would the other one have to be to make this work. Well, to get 7x, we would need to have a 7x here. Sorry, to get 7x squared, we would need a 7x there. And to get a 6 here, we'd have to have what here? Well, 3 times 2 gives us 6. Okay, so I'm guessing that's it. And then rather than do all that thinking and trying to factor it on our own, just do it this way and then see if that works. Does this give us the right middle term? Let's see, x times 2 gives us 2x. 3 times 7x gives us 21x. 21x plus 2x, yeah, that's 23x. So it does work. So if you factor the easier one first, it gives you an idea of what you can expect for your answer. Okay, and then, well, they both got that x plus 3, so we can cross those out. And then what's left here? 7x plus 2 on top over x minus 1. Okay, so again, if you look at something that looks hard to factor, factor the easier part first, and then hopefully that tells you what might be one of your factors. All right, next one here. 32a cubed over 16a squared minus 8. Okay, let's see. I'm going to factor the bottom first, and you'll see why on top in a minute. But if we factor the bottom, 16a squared minus 8a, what do those have in common? Well, I can take out an 8 and an a. And then what's that leave me with? If I take out an 8 and an a, I get 2a minus 1. Okay? And then let's see, I got an 8 here, so I'd like an 8 on top that I can cancel that with. And then, yeah, we can rewrite this. Instead of 32, how about leave it as, and it doesn't have to be completely factored, but how about 8 times 4? That's the 32 part. And then the a cubed, I'm going to write that as a times a squared. Okay, now that's kind of a funny way to write it, but I like having an 8 on top and bottom so I can get rid of those. I like having an a to the first on top and bottom so I can get rid of those. And now I can clearly see what's left over. We've got 4a squared on top over 2a minus 1 on bottom. Okay, and then I'm done. And again, I can't reduce the 4 and the 2 because this isn't 2, it's 2a minus 1. Okay, this is all one thing. Okay. All right, last one on this first page here. Then we got a few more on the next page. Okay, here, x cubed plus 125 over x plus 5. Okay, so then this is going to be a sum of cubes factoring problem. So here we just got to use the formula. And if we use the formula, keeping in mind that the cube root of the first part is x, the cube root of the second part is 5. Okay, so in my formula, wherever I have an a, I'm going to put an x. Wherever I have a b, I'm going to put a 5. This is going to factor to x plus 5, which we expected because that's all that's on the bottom. And then times x squared minus 5x plus 25. Over, the bottom didn't change. All we have is x plus 5. Okay, we can put them in parentheses if we want to. We don't have to, though. And then these are going to reduce to 1. So all I'm left with is that trinomial, which is our answer. I'll just rewrite it here. X squared minus 5x plus 25. Okay. Oops, low there. All right, so this section, as you can see, is mainly just a bunch of factoring. The rest of the stuff is fairly simple. Okay, let's see a few more problems on the next page. Keep this down to one video here. All right, let's zoom out so we can see the whole problem. Now, sometimes they're going to give us our problems in function notation, which they've been doing throughout the whole year, so hopefully it's nothing new. Hopefully you're used to it by now. All right, so they want us to find f of g of x, sorry, f over g of x, if f of x is this thing and g of x is that thing. Okay, well this just means f of x over g of x. Okay, so f of x is this function right here, m squared minus n squared. And then over g of x, which is m squared plus 11mn plus 10n squared. All right, so there is our polynomial expression, our rational expression. Okay, so I want to factor top and bottom. Well, on top we've got a difference of two squares. Instead of a squared minus b squared, they just use different letters. But that's going to factor to m plus n times m minus n. Okay, sorry about my handwriting. M's and n's, they kind of look similar with me. All right, and on the bottom, we've got m squared plus 11mn plus 10n squared. All right, well, it's a trinomial, so I know it's going to factor into two binomials. Okay, my signs are the same and they're both positive. So plus and plus. So you can probably already figure out now what's probably going to be one of the factors on bottom. Most likely m plus n. Let's see if that's the case. Yeah, to get m squared, I do need an m and an m. Okay, and then to get 10n squared, let's see. What multiplies to 10 and adds up to 11? Well, 10 and 1. So then I'm going to have a 10. Well, it's got to be 10n squared, so 10n and 1n, which we don't need to write the 1 in front of the n. Okay? But yeah, if I multiply this out, I will get this trinomial here. Okay, so we got that thing completely factored. They both have m plus n on top. So then our answer is going to be, and we don't even need to rewrite it. It's going to be right there, m minus n over m plus 10n. Okay? All right, so you can probably see why I like using x's and y's better than m's and n's. Okay, moving on, two more to go. Okay, this one, there's a lot going on here. Before we start, we're trying to reduce anything, because that's an option. You know, there's not always one particular order you have to do things in, but let's expand this stuff first. Okay, so using our distributive property for exponents, I want to distribute this exponent to both of those two terms there. So then that would give me x cubed y cubed. And then same thing here, I want to distribute the 4 to the two exponents there. So that would be times x to the 4th, z to the 4th, and then I got another y to the 4th. Okay, so then that's on top. Next, I want to just do the same thing on the bottom. Distribute the 2 here, that's going to be x to the 4th and y squared. And then same thing here. Multiply those exponents, we get z to the 4th and x to the 4th. Okay. Now the next part you do, the order is up to you. I can combine all the x's and y's and z's up on top and do the same thing on bottom, so I only have x one time on top and x one time on bottom and so on. Or you can start crossing off things you see in common. Let's simplify first by combining like terms. X to the 3rd times x to the 4th, I get x to the 7th. Okay. We'll go in alphabetical order. Y to the 3rd times y to the 4th is y to the 7th. And then z to the 4th is my only term on top with z in it. Over, let's scoot this over so we can see. X to the 4th times x to the 4th, we get x to the 8th. Y squared is the only y term on bottom. And then z to the 4th. Okay, and then now we can start reducing. Now another option, if this is confusing, I can write x times x times x times x, 7 times. And I can write y 7 times, and I can write z 4 times, and completely expand this. But we don't need to do this. We know our exponent rules. We can just, add and subtract. Okay, so here if I have 7 x's on top and 8 x's on bottom, well, all of these are going to cancel with 7 of those, and I'm going to have 1 left on bottom. So I'm going to have at least an x on bottom. Okay, and then if I have 7 y's on top and 2 y's on bottom, well, both of these are going to cancel with 5 of those. I'm going to have 5 y's left on top. Okay, so it's just our exponent rules where, when we have a y to a power over y to a power, we subtract the exponents. Same thing here. And then z to the fourth over z to the fourth, well, those are going to reduce to 1, right? I got z to the fourth divided by itself. Anything divided by itself is 1. And we're left with y to the fifth over x to the first. And that's our answer. Okay, so again, you didn't need to go in that order, but I can't do the problem 5 different ways. The video would take too long. Okay, but this works. All right. And then the last one. They want to know, when is the following expression true? Always, sometimes, or never? Okay, well, before we can answer this, we need to simplify this stuff, especially the left side. The right side of the equation is pretty much, already simplified. We can't do anything with that. But what can we do over here? Well, let's see, on top left, we've got a 4-term polynomial. Let's try to factor that by grouping. Okay, so in fact, we'll do it off to the side so we can show our work. If I want to factor this thing by grouping, let's rewrite it first. 3xy minus 2x plus 24y minus 16. Okay, so if we have this 4-term polynomial, we want to group the first 2 terms together and then see what do they have in common. Just an x, so we can take out an x, and that leaves us with 3y minus 2. And then next, what do our last 2 terms there have in common? Well, they both have a GCF of 8. I don't want to change the sign. I like that it's negative, so I'm going to take out a positive 8. Okay, and then that leaves us with 3y minus 2. All right, and then since these both have a 3y minus 2, because again, this is just a big binomial, I've got this big thing plus that big thing. They both have the 3y minus 2 in common. So I'm going to take that out, and that would leave me with just the x plus 8. Okay, so I can replace this big 4-term polynomial with just these 2 binomials. Okay, so we'll write that. We get 3y minus 2 times x plus 8 over, and then how can we factor the bottom? Now we can probably just do that right here. I know it's going to be 2 binomials since this is a trinomial. Let's see, I got to have x and x to get x squared. My signs are the same, they're both positive, so plus and plus. And then what multiplies to 8 and adds up to 9? Well, 1 times 8. Okay. All right, and then before we set it equal to this thing, let's completely reduce this one. They both have an x plus 8, so I can reduce those, which leaves me with 3y minus 2 over x plus 1. And we want to know, when is that equal to this thing, which is 3y minus 2 over x plus 1. So then when does 3y minus 2 over x plus 1 equal 3y minus 2 over x plus 1? Okay, well, it's definitely not never, because, I mean, they're equal, right? They're the same thing, so we can cross that off. Now, is it always or sometimes? Okay, well, the answer is sometimes, and the reason is, and it's something that we haven't been pointing out on most of these problems, but what can x be? Almost anything, right? Because it doesn't really matter what's on the bottom unless it's a 0. Okay, and is there ever a time that x is going to be 0? Yes, because x cannot equal -1. Okay, so it can be anything except for -1, but I mean, it's a ton of numbers, but it's not always, because here's when it can't be. So anyways, even though it's just one thing that it can't be, that is why it is sometimes these 2 things will be equal. If x is anything other than -1, those 2 statements will be equal. But if x is 0, well, then that's undefined. Okay. All right, so pay attention to that, because again, it's not something that we really talked about. But if you get a problem just looking at a random one, like how about the last one we did on the first page? Okay. If they want you to simplify, more specifically when we're solving a little bit later on, you're going to have to list the excluded values. Okay, x cannot be -5. That would make that denominator come out 0. Okay, what about here? X cannot be 1. Is that the only thing that x cannot be? Well, no, because we always want to look at our original statement. X can't be 1 and x can't be -3, because that would make this thing come out 0. So it's not just our answer, it's our original problem. We'll talk about that more when we talk about solving, but that wraps up the first notes video.